Hello everyone. Today we're going to be starting a new unit on exponential models or exponential functions. So today we're going to look at graphing exponential growth and decay. So this is a little tie back to some Algebra 1 experience. You're going to need to take some notes, obviously, today. 3 graphs we're going to do. A calculator is especially handy, maybe even your graphing calculator app, and something to write with. Okay, so let's first start with an idea of what would I rather have, or what does it mean to grow exponentially? So let's pretend that I have option A, where I'm going to give you $10,000 every day for the next 30 days. And then there's option B, where you're going to take a penny today, but I'm going to double it every day for the next 30 days that you walk in. So if we look at option A, look at how this changes over 10 days. Day 1, I'd have $10,000. Day 2, I'd have $20,000. Day 3, I'd have $30,000. It's a constant amount of increase. We're increasing $10,000 every day. Whereas option B starts with one single penny, and then progressing forward, at the end of the 9th day, I'd have 512 pennies. That's right, that's $5.12. And here, I'd have $90,000. Do you think that option B would ever catch option A? Do you think option B would ever be a better choice? The answer to that is yes. In fact, if we were going to figure out how much I would have after 30 days, remember each time I am multiplying by 2. So there's an increase of 2 here, but an increase of 4 there, an increase of 8 there, an increase of 32. This is not a constant increase or a constant slope. Because of that, this is exponential growth, okay? This is an exponential growth idea. To find out how much I would have in terms of pennies, how many pennies I would have, I would take 2 to the 30th power. I'd keep multiplying by 2 for 30 days. That would be how many pennies I have. That's a lot of pennies if you type that in your calculator. So this idea of things that exponentially grow or decay, they're things that grow or decline at a certain rate. Please write this part into your notes. That rate is a percent that we're looking for, okay? An idea, a percent, not a constant amount like $10,000, but a percent, like I'm growing at 50% or shrinking at 40%. Things that do this might be your bank account, population, radiation, depreciation in your car, carbon content of fossils. So this idea of exponential growth or decay is something that's applied in many places, especially in math and science, and then also in economics. So the graphs we're going to be looking at today are going to look like this. They're not going to be straight lines because that would indicate I have the constant slope factor, and I don't. They're going to be swooping up like this or decaying on the other side, starting high and then kind of swooping to the right low. So our goals will be that you can graph these very carefully, that you can identify the domain and range as always. And today we're going to learn about a new thing called an asymptote and be able to identify them on our graphs. So let's start again in your notes right here with this general equation. Okay, it says y equals, that y could be an f of x, a times b to the x power. Notice that the b is the base of the exponent, okay? So the x is only taking the b to that repeated power. This is what our exponential growth and decay equations functions are going to look like. How do we tell if things are growing or decaying? It's all about that b that has the exponent. So it's an exponential growth function if b is greater than 1. The b is called the growth factor. That's the thing that makes it grow. So an example problem would be like y equals, here's my 1 penny, and I'm going to keep doubling it for however many days or years that we would want. So this, because the b has been replaced with a 2, is growing because that b value is greater than 1. Exponential decay functions will happen when I have the same general setup. Maybe there's a 1 in front or a 5 or something, but now the b, the thing that has the power, the base, is between 0 and 1. Okay, so like 3/4, 1/3, 2/3. This is what we're looking at when things are decaying. That means it's taking 1/3 of something repeated times. It's like division over and over and over. So that's decaying. That's called the decay factor if that b is between 0 and 1. So our graphs today are going to have that general sort of idea that b is going to be there. We're going to have an a amount out in front like we just saw. This is the first one you need to get into your notes. So we have f of x equals 3 times 2 to the x power. And to make a good graph of this, we're going to make a table. This is where either your graphing calculator tool comes in handy, or you choose some x values that we're going to plug in. X and Y, nice little table. We're going to plug in maybe -2, -1, 0, 1, 2, just some general x values into that function up there. So for this first one, if I plug in -2, it would look like this, 3 times 2 to the -2 power. Be careful, only the 2 has the exponent, not the 3, so it's not 6 to the -2. It's 3 times 2 up to the -2 power when you type it in your calculator. And be careful, your calculator will probably give you a decimal here. This decimal is 0.75. Okay, and we'll do the same thing with -1. I'll just retype this here, 3 times 2 to the -1, and we'll ask the calculator what that value is, 1.5. 0, if we type that in, 2 to the 0 power is 1 times 3 is 3. And then if we do 3 times 2 to the first, 2 to the first is 2, times 3 makes 6. 3 times 2 squared, that's 4, times 3 makes 12. So if we go ahead and we plot this, we should see exponential growth or decay. Can you tell which one it is? Yes. The B, the thing that has the exponent, the base, is 2. And because that's greater than 1, we are going to be seeing a growing model here, or so, a graph that's growing. So at -2, I'm up 0.75. -1, I'm up 1.5. 0, I'm all the way up to 3. 1, 6. And 2 off my graph at 12. So this is that sort of swooping idea. It's definitely growing really rapidly there on the right-hand side. See this where we started our first dot right there? Is that the actual start of the graph, or do you suppose that I could have plugged in -3, -4, -5, and so on? The answer to that is I could plug in any numbers I want here. I could plug in -3, -4, -5. That whole idea would be happening here. This is just the beginning of our table. That -2 is just where we decided to start our table. So if I would say have chosen -5, I could do that. It would just be probably a really weird sort of decimal answer here. So 3 times 2 up to the -5 power is 0.09. That's really, really close to 0. So see what's happening? The farther I go to the left here, this is really hovering right above that x-axis, okay? He's not going to give us a negative value. He's going to hover right above there. This idea that there's a leveling off spot on the graph where the function doesn't really ever cross or touch, but he stays right above. The line that this function stays right above is right here. He's hovering on that left side right above that line. This is called the asymptote. Okay, the asymptote. The line that kind of has that function levels off there on the left-hand side, that's the asymptote. It really gets really close to it, but it never really touches it. So the asymptote for our graph, the new thing that we're going to add, besides domain and range here, is our asymptote is going to be a part of something we need to describe. And the asymptote here would be where y equals 0. Because that line, that red line that I drew, is going through the y-axis at 0, horizontally there, the asymptote is at y equals 0. My domain is all the x values. Now we just got done saying you could have chosen any x values you wanted in the world. So our domain continues to be all reals. The range values, however, notice that the entire blue graph of that function there stays above that asymptote. So that means that my range is going to be greater than, or not equal to, people. We never touch it. It's greater than the 0. Okay, so greater than the 0. Y has to be greater than 0. It's going to stay above that asymptote, never really touch it. So asymptote is a new idea for us. So what is an asymptote? Maybe you want to write that definition in your notes. The asymptote is a line that a graph approaches more and more closely but never truly touches. So it's a leveling off that we're going to see. You can see on this graph the leveling off appears to be leveling right above that 3 right there, or right at 3. So the idea that the asymptote would be where y equals 3, and then I'd say my range, my whole graph stays above that 3 mark. Okay, so that asymptote is a new idea for us. Let's go and graph, oops, let me see if I can get back. Let's go and graph our next example here. We have y equals 2 to the x minus 3 and then subtract 5. So I'm going to make an xy table again. And again, I'm going to just choose x values to plug in right there. So maybe it's negative 1, 0, 1, 2, 3. I mean, choose some x values there or use your graphing calculator. Here we go. And then minus 5 here. And we're going to go ahead and take a little look here at what those x values would give us for y values. So if I look at negative 1, if I plug in negative 1, it's 2 to the negative 1 minus 3 minus 5. This is 2 to the negative 4 power, that means. And then subtract 5 from that. So if you calculate that in your calculator, you should end up with negative 4.9. And then if I do 0, I get negative 4.875, which is pretty much 4.9 again. And then 1, I get negative 4.75. And 2, I get negative 4.5. And 3, I get negative 4. And if I kept going, for 4, I'd get negative 3. 5, I'd get negative 1. There are all kinds of nicer points I could graph later on here. So if I take negative 1 down negative 4.9. Woo, he's way down there. 0, down 4.8. 1, 4.75. 2, negative 4.5. Pretty level there. 3, up to negative 4 now. 4, up to negative 3. 5, up to negative 1. Look at that. So if you can see this graph here, it's again a growth because the 2 is the base, okay? But the leveling off spot, or that asymptote, has now changed. The asymptote now would be where y equals negative 5. Again, the leveling off happening right here. Gets really, really close to that line, but never really touches it, okay? So y equals negative 5 is that asymptote. Our domain, any number I wanted to plug in, I could. Okay, any number I wanted to plug in, I could, so that's all reals. My range, however, the graph stays above that negative 5 mark on the y, so my range values are going to be above negative 5. So my y values are greater than negative 5. Not greater than or equal to, just greater than. It never really touches that asymptote line, okay? So let's do one more example. This one appears to be a decay. Do you see how we know? Instead of having a 2 or a 3 or a 4 there, I have something, a base value between 0 and 1, a 1/5. That's going to make this thing decay. So I'm going to use my XY table here. And we're going to choose some values. Maybe again, negative 1, negative 2, whatever here. I'm going to put some 0, 2, 3. And then we're going to go ahead and plug those in. So 1/5 to the negative 1 power plus 1. And we'll use our calculator now to generate that list of values for us each time. So when I typed in negative 1 here, that was my delay, negative 1, 6 is what I have there. If I take 1/5 to the 0 power, which is 1, plus 1 is 2. Okay, continuing on, when I type in 1, 1.2. When I change that x value up there to a 2, 1.04. 3, 1.008. So if I make a little plot or a little graph, negative 1, I'm up at 6, 0, 2, 1, 1.2, 2, 1.4, 3, not quite, a little bit above 1. Now notice, this time with decay, it started out high on the left-hand side and now is ever shrinking really, really, really small and leveling out over here. Where's the asymptote? Right here. That graph is getting really, really close, approaching that y equals 1. So my asymptote is at y equals 1. My domain, what x values could I plug in? Anything I want. And my range value, again, I'm staying above that asymptote. So my range values are y is greater than that 1. So how can you tell where the asymptote is? Just by looking at the equation. Do you see the pattern? I hope you do, because there's a pattern to know where that asymptote line is going to be, okay? So we'll continue graphing in the days to come. Thank you for taking good notes.